Second-order RLC circuits. Let's break down what they are, how they behave, and why every electrical engineering student needs to understand them. An RLC circuit contains three passive components. R, the resistor, dissipates energy as heat. L, the inductor, stores energy in a magnetic field and resists changes in current. And C, the capacitor, stores energy in an electric field and resists changes in voltage. Why do we call it second order? Because when you write the equation that describes this circuit, you get a second-order differential equation. That second derivative appears because there are two energy storage elements, the inductor and the capacitor. Compare this to a simple RC or RL circuit, which has only one storage element and gives a first-order equation. To solve the equation, we form the characteristic equation, s squared plus 2 alpha s plus omega naught squared equals 0. Alpha is the damping factor, determined by R, and L omega naught is the natural frequency, determined by L and C, and the damping ratio zeta, which equals alpha over omega naught, tells us exactly what kind of response we'll get. There are three possible responses. When zeta is greater than 1, we get an overdamped response. The circuit returns to steady state slowly with no oscillation. When zeta is less than 1, we get an underdamped response. The circuit oscillates while gradually decaying. And when zeta equals exactly 1, we get a critically damped response, the fastest possible return to steady state without any oscillation. So why do we study second-order RLC circuits? First, they are foundational. They teach the core math and intuition needed for more complex systems. Second, they explain filtering. Every bandpass, low-pass, and high-pass filter builds on RLC behavior. Third, resonance. Understanding it is essential for radio, wireless charging, and power systems. And fourth, control systems. The same differential equation describes mechanical springs, shock absorbers, and feedback loops. RLC circuit behavior shows up everywhere. Radio tuning, power supplies, signal filtering, car suspension systems, audio equalizers, wireless charging, medical devices, and antennas. The math behind these circuits appears in virtually every branch of engineering.